Hello and welcome to today's video. In this video, we're going to introduce the notion of sequences. Now, a sequence is a mathematical model for a discrete time process. What is a discrete time process? Well, that is a function that evolves in discrete steps, meaning, for example, measurements are only taken in certain time intervals, or changes only happen in certain time intervals and not on a continuous scale. One example is the growth of capital through interest. Usually, if you have an account that gets interest, then this interest is paid on a yearly basis, or maybe per quarter or per month. It's not paid in a continuous way. So this is a discrete time process. Also, paying annuities is a discrete time process. If I'm paying back a loan in annuities, then I usually do this every month, or maybe every week, or every year. Again, discrete time steps. I'm not continuously paying back my loan. There are also some phenomena in nature that are modeled on a discrete time scale, although they don't really take place on a discrete time scale. One example is radioactive decay. Now, of course, that is not something that happens discretely, but on a continuous time scale. But usually measurements are only taken in certain intervals. For example, you would be interested in the amount of radioactive material that is still present after a certain number of years, and you would take yearly measurements or maybe daily measurements. You would not be interested in the actual continuous process here. So in this case, the continuous timescale is not really important to the application, and you only measure and model on a discrete basis. And that's something where these sequences come in. And basically a sequence is just a function that maps the natural numbers, including 0 in most cases, to some real number. So what we have is a sequence of real numbers, and they are indexed, if you want, by a natural number as an index. So in this video, we'll start with the definition and also with some notions surrounding this definition of sequences. So this section is called sequences. And as I've said already, the idea here is to provide a mathematical model for discrete time processes. For example, something like capital growth through interest. That is paid, let's say, once a year. Or also, if you look at the stock market, if you have historical data for the stock market, then usually you will have one stock price per day. So the resolution here is days, right? And that means we also have discrete time steps in this case. Or I also mentioned radioactive decay. With, let's say, yearly measurements. And in this case, of course, the process itself might not be discrete. That might be a continuous process, but we discretize it because we're only interested in that resolution. So once a year is sufficient for a certain application, and that means we're only interested in that data and not in the actual continuous process. So what is the definition of a sequence? as I said, basically a sequence is just a function that maps the real numbers to some, that maps the natural numbers to some real numbers. So a function, let's call it A, that maps n0 to the real numbers R, is called a sequence. And there's a special notation for sequences that we'll also introduce. We usually use the notation A with an index n to mean the nth element of a sequence. So that is the function value at n. So that's for the nth element of a sequence. And for the sequence itself, we usually use the notation an in brackets, and then as an index, we write the index set like this, n and n0. Or we sometimes abbreviate that a little by writing an and then just the index set like this. So this is an abbreviation for the sequence A. And of course, other index sets are possible as long as they are discrete. Usually subsets of n0 are often used for sequences. So for example, you can opt to start a sequence at 1 instead of at 0, or at 75 if that makes sense for some reason. That's all fine. Sometimes you'll also encounter sequences that allow for negative indices. So in that case, set, all integers would be the index set. But well, that will not often be the case. Usually we use n or n0. Some notions surrounding sequences. First thing I'd like to define is what a bounded sequence is. And that simply means the values of that sequence do not exceed some bound. And of course, the values may also be negative. So we look at the absolute value. Meaning the sequence values do not exceed a bound in the positive numbers, so they're bounded above, and also in the negative numbers, so they're bounded below. So we'll say a sequence an with index set n0 is called bounded. If there exists some bound b in the real numbers, with the absolute value of an is less or equal to that bound b for all values of n in the index set. So it's bounded above and below. Then, of course, the values of a sequence can be compared as they appear. So the index set imposes an order on those values, and then we compare subsequent values to see if they increase or decrease, or maybe they alternate. So in particular, we want to define what it means for a sequence to be increasing or decreasing. So a sequence an n0 is called possibly strictly increasing or strictly decreasing or just decreasing. if the following condition holds. For an increasing sequence, as you can imagine, an plus 1 needs to be greater or equal to an, or strictly greater to an for strictly increasing, and that needs to hold for all n in the index set. And for decreasing, it's just the reverse sign, so you want an plus 1 to be less or equal to an. That would mean the sequence is decreasing, and again, strictly less than for strictly decreasing. And again, that needs to hold for all n in the index set. And finally, as an abbreviation, we call a sequence monotone or strictly monotone if it is either increasing or decreasing or strictly increasing or decreasing. So often it's just important to know that a sequence is increasing or decreasing, and it's not really important whether it's increasing or decreasing. That's when we say a sequence is monotone. So a sequence is called monotone or strictly monotone if it is strictly increasing or strictly decreasing. Okay, so that's the definition of a sequence and some of its properties. As usual, let's have a look at some examples before we proceed. A very simple example. Let's define the sequence an through 1 plus 2n. And that's one way to define a sequence. You can just write down a formula, a functional formula here, so that you can compute every element of that sequence directly. So in this case, that sequence an(0) would then consist of the numbers 1, that's for n equals 0, n equals 1 would then be the number 3, and we have 5, 7, and so on, right? So this is n equals 0, this is the case n equals 1, n equals 2, n equals 3, and so on. So what this sequence is, it's the sequence of positive odd numbers. And as you can see, this sequence is increasing, and in fact it's even strictly increasing. And also it's unbounded. It will surpass any bound that you may suggest. I can always name, for any bound that you name, I can always name an odd number that is higher than that. So this is unbounded. It would of course be bounded below, right? There's no element of the sequence that is less than 0, for example. So 0 is a lower bound, but there's no upper bound. Another sequence that you will encounter often, that is a generalization of this here, is the so-called arithmetic sequence. What that means is a sequence of the form an equals some initial value beta plus an increment alpha times n, with alpha, beta, some real numbers. So that means you start with beta, and then you increase by alpha, and then you again increase by alpha, and so on and so on. Right? So this odd numbers, for example, A is a special case of this one. For beta equals 1, and alpha equals 2. So you start with 1, and in each step you increase by 2. Okay, so this is a sequence that is strictly increasing if the alpha is positive and strictly decreasing if the alpha is negative, and it is unbounded. So strictly increasing for alpha positive, and strictly decreasing for alpha being negative. Now, strictly increasing or decreasing does not necessarily imply unboundedness. For example, if you have a look at the following sequence, an equals 1 over n, and now we need to restrict n to the natural numbers without 0, because division by 0 is not possible. So what we get here is the sequence 1, 1 over 2, 1 over 3, 1 over 4, and so on. So you can see this is a sequence that is strictly decreasing. But it's also bounded, because obviously an is in the absolute value always less or equal to 1. Or more precisely, you could also say an is somewhere between 0 and 1. Okay, so that's an example for a strictly decreasing but bounded sequence. Next example, it's also a sequence that you'll encounter very often, that is called the geometric sequence. So if we define an to be equal to alpha times q to the n, where alpha and q are real numbers. For example, you could have a sequence like an equals 1 over 2 to the n, right? So then q is 1 over 2 and alpha is 1, right? So there's an implicit 1 here. And that means simply this sequence has the values 1 for n equals 0, 1 over 2, 1 over 4, 1 over 8, and so on. So the value is halved in every step. And this, of course, is strictly decreasing in this special case here, as we have q between 0 and 1 and positive alpha. It will be strictly increasing for q strictly greater than 1. And in this case, you can also see it's bounded because the sequence is between 0 and 1. And finally, let me write down a famous sequence that we'll also encounter numerous times. There's the so-called Fibonacci sequence, or the Fibonacci numbers. Those will usually be denoted by f, sometimes a capital F. And this is defined in a recursive way, meaning I do give the initial value, so the value of the first and maybe the second sequence element, and then I provide you with a formula that calculates the subsequent sequence elements from the ones I already have. So in this case, I will provide the first and second element, so I'm saying f0 is 0 and f1 is 1. And then the next sequence element from 2 on will be defined as the sum of the two previous elements. And that's why I need two initial elements, right? To compute f2, I need f1 and f0. So this will work for n greater or equal to 1. That is the recursive part here. Okay, so what do we get? Well, what that means is f2 is equal to 0 plus 1, that's 1 again. Now f3 would be equal to f2 plus f1, so we get 1 plus 1, that's 2. f4 would be equal to f3 plus f2, so 1 plus 2, that's 3. Then we get f5 equals to 2 plus 3, so we get 5. f6 equals 3 plus 5, that's 8. And you can see this is picking up speed, so f7 would be 5 plus 8, so that's 13 already, and so on and so forth. So again, the sequence is increasing. But not strictly increasing. You have hopefully noted that we have f1 equals 1 and f2 equals 1, so that's why it's not strictly increasing. That's the only exception to the strictly, indeed. And it's also unbounded. And we don't have an explicit formula for that sequence here. Surprisingly, there is actually an explicit formula for that sequence. And we'll try to derive that later on in Math 2, when we talk about some interesting linear algebra facts that will enable us to derive such a formula. So this completes the introduction to sequences. In the following videos, we talk a bit more about details, and in particular, we talk about sequence convergence, so the question of long-term behavior of sequences. I'll see you then.